So you remember that we were discussing this thing called the de Laval nozzle, which is really something that was initially thought of in engineering circles, and in doing so we essentially came up with this equation, which relates the so this is a purely one-dimensional flow. Okay, so this equation essentially relates the velocity and the derivative of the velocity with the area and the derivative of the area. And an area of what? Well, area of the pipe, right? The area of the pipe can be varying like this, right? The cross-sectional area, right? So this is what we're talking about, and it can vary as a function of x. So A can vary as a function of x. And the question we were asking is how, and this is the Mach number, of course, right? So the question we were asking is, how does the flow behave with the change in area as it passes, and does it conform with intuition, right? And what we found out was, well, let's first consider subsonic flows for in other words, the case where the Mach number is less than 1, right? So, and we find out the area itself is always larger than 0, isn't it? So when, for instance, when dA dx is less than 0, in other words, the channel, the area is pinched like this. It's somewhat like you're pinching, a garden hose. So the area is decreasing, which is what this is. When the area is decreasing, you expect that the fluid flow, the fluid squirts out at a higher speed here, as compared to the speed here, right? And that is really what happens here. You see, when m squared is less than 1, m is less than 1, this quantity is negative, and what happens is this quantity is negative. Therefore, when this quantity is negative, then this has to be positive. Okay, so the flow accelerates when dA dx is less than 0, and the flow decelerates when dA dx is greater than 0. For a diverging nozzle, this is also something. So in this case, dA dx, in this case, and in this case, for this, and in this case, dA dx is greater than 0. And so we normally, expect that flows when the cross-sectional area is increased, the flow decelerates, and then when the cross-sectional area is decreased, in other words, for instance, if you pinch the pipe, the flow accelerates, and that it's okay. I mean, as long as the Mach number is less than 1, that behavior is indeed reproduced. The thing is, though, so subsonic flows do conform to intuition. But what about supersonic flows, right? And we find some strange behavior in supersonic flows. We find that because m is greater than 1, and this is always positive, right? So the signs of du dx and dA dx are the same, because a and u are all positive, so there's no scope that this can change signs. So if dA dx is negative, in other words, in a situation like this where the channel is being squeezed, you find that the flow decelerates. So dA dx is negative, and du dx is also negative. So the flow decelerates in a converging channel, which is opposite to our intuition about subsonic flows. So for supersonic flows, it's strange, right? And if dA dx is positive, in other words, like this, if dA dx is positive, du dx is also positive. In other words, the supersonic flow accelerates in a diverging channel, right? So this is the strange thing about supersonic flows, and we will see what connection this has. We will explore this a little more, and then we will go on to see what connection this has to astrophysical jets, right? Okay, this is what one would call a nozzle. On the left hand side, these are all, and these are what are called. A nozzle is something that as the name implies, it increases the speed of the flow, right? And a diffuser is something, as the name implies, something that decreases the speed of the flow and spreads the flow around. For instance, if you were trying to spray paint something, you don't want a nozzle, right? If you're trying to spray paint, what you do is you inject the paint at high velocity, and then you want the paint to diffuse when it flows out, so that the droplets nicely diffuse and they cover a large area. So that's what a diffuser is, right? So for Mach number less than 1, this would be a nozzle. What would be a nozzle for Mach number less than 1? This kind of situation where dA dx less than 0, right? You see the dA dx is indeed, the area is decreasing as a function of x, so this would be a nozzle, and this would be a diffuser. In this case, the cross-sectional area is increasing, in other words, right? So this would be a diffuser. Why is this a diffuser? Because as subsonic flows pass through a diverging channel, their speed decreases and the flow diffuses, right? So this conforms to intuition. For supersonic flows, however, it's this kind of a thing where dA dx is actually greater than 0. It's a diverging channel. Okay, it's this kind of a diverging channel that acts as a nozzle. In other words, supersonic flows accelerate when they pass through a diverging channel. Therefore, a diverging channel acts as a nozzle for supersonic flows. Here, okay, like this. The top half is for subsonic flows where Mach number is less than 1, and the bottom half is for supersonic flows where the Mach number is larger than 1, right? So when the Mach number is larger than 1, contrary to intuition, it's this kind of a diverging channel. In other words, a situation where dA dx is greater than 0, that acts as a nozzle, and in this kind of, it's this kind of a converging channel where right, the area decreases as a function of x. This situation acts as a diffuser. It's exact opposite of the situation for subsonic flows, right? So just wanted to emphasize that a little more before we proceed. And now let us go ahead. Finally, putting these two things together. This is what's this is what's normally called the de Laval nozzle. Okay, so what you have is a pipe whose cross-sectional area is decreasing here until it reaches a throat, and then it increases. Okay, and so in this region up until here, okay, and from here to here, here onwards, right? And right here, exactly here, is equal to 0. It's less than 0 to the left, is equal to 0 exactly at this point called the throat, right? So this is called the throat, right? So exactly at the throat, it's equal to 0. The derivative of dA dx is equal to 0, and to the right of the throat, dA dx is larger than 0. So this is the situation. So imagine you have a subsonic flow. right? So a subsonic flow would have Mach number less than 1, right? So a subsonic flow is passing through a nozzle, right? It accelerates. In other words, the Mach number is initially less than 1. It becomes larger and larger because it's accelerating. We are assuming that the sound speed remains constant, of course. Okay, the sound speed does not change. The speed of sound is the same. So if the flow is accelerating, well then, and if the sound speed is the same, it remains constant, then naturally the Mach number is increasing. It's increasing from less than 1, and it comes to a point where at the throat, the Mach number is exactly equal to 1. Okay, and beyond that, what happens is, the flow continues to accelerate. So beyond here, what happens is anything beyond here, anything beyond Mach number equal to 1 becomes Mach number larger than 1, of course. And we know that for supersonic flows, a diverging channel is a nozzle, isn't it? So to the right of this, you have supersonic flows. And for supersonic flows, the diverging channel is a nozzle. So the flow continues to accelerate and the Mach number becomes larger and larger. So all the way from to the left to the right, the Mach number is increasing. Okay, the Mach number was initially less than 1. It passes through 1, and then it becomes greater than 1. All through, the Mach number is increasing. Okay. All the way from left to right, the Mach number keeps increasing. But the shape of the nozzle is different on the left and the right. Why is that? Because on the left, the flow is subsonic, and therefore, in order to increase the Mach number, or in order to more accurately, in order to accelerate the flow, and therefore to increase the Mach number, you have to have a converging channel. Okay. Whereas on the right, once you pass what's called the sonic point, so this is, in other words, U over C sub S is equal to 1, right? And so this is called the sonic point, for obvious reasons, right? The flow speed is equal to the sound speed. So this is, right at the throat, you have what's called the sonic point, right? And to the right of this, the flow starts becoming supersonic. So if you have to ensure that the flow keeps accelerating, and therefore the Mach number keeps increasing to the right, also you need to have a diverging channel now, because we know that for supersonic flows, a diverging channel acts as a nozzle. Right. So this is this clever, situation where you have, the Laval nozzle is this clever situation where you ensure that, so essentially, the Laval nozzle ensures that the flow keeps accelerating as it passes from subsonic through the sonic point which is right to supersonic, which is right. So let me do this one, and let me show you this once again. So the de Laval nozzle is a device which ensures that the flow keeps accelerating as it passes from a subsonic flow through the sonic point where m equals the Mach number equal to 1 to supersonic. So this is what a de Laval nozzle does. Importantly, so this is an example of a transonic flow. Why transonic flow? Because it's something that transitions. This is a flow that transitions from being subsonic through the sonic point into supersonic. Okay. Importantly, the sonic transition, in other words, the transition through the sonic point where m equals 1 is smooth, i.e., no discontinuities. Such as shocks. This is very important. It's not just that a de Laval nozzle is not just a device that ensures that you pass smoothly from a subsonic flow to a supersonic flow. Yes, that is one thing, through a sonic point, but also it's a device that ensures that this transition happens smoothly. Okay, so you have to engineer the DADX very carefully. Okay, the throat has to be, the throat. This one, I mean, there are many ways in which you can transition from a DADX less than 0 to a DADX larger than 0, right? I mean, the converging nozzle can be very sharp, for instance, and the diverging nozzle can also be very sharp. But you have to engineer the shape of the nozzle such that you ensure that that the transition happens smoothly without any discontinuities such as shocks. This is very important. You can transition from, remember, one can transition from greater than 1 to less than 1 through a shock. One can do that. Okay, but a de Laval nozzle is something that does not do it this way. It ensures that the transition happens smoothly. Okay, right. So having emphasized this, let's go on. Yeah, so the sonic point happens where the DADX is equal to 0, right here at the throat, right? Okay. Now, what does again, just to re-emphasize what we were saying, the de Laval nozzle is a device which effectively accelerates a high temperature, high pressure flow. Well, a high temperature, high pressure, low velocity. In fact, the high pressure and low velocity kind of go hand in hand. Okay, it's the flow. It's most of the when we say high pressure, what we're really saying is most of the energy is an internal energy of the gas. Okay, that's the same thing as saying high temperature. Okay, this and this ensure that most of the energy is in the internal energy of the gas, and that it converts, and the de Laval nozzle is something that converts this kind of a high temperature, high pressure, low velocity gas to a high velocity gas. Okay, in other words, the internal energy is converted into the kinetic energy of the bulk flow. That's when you get high speeds, and specifically the speeds are supersonic. It was originally designed for steam turbines, and it's now often used in rocket engine nozzles and supersonic jet engines. Unfortunately, I don't know how many of you would have heard about supersonic jet engines. Long ago in the 80s, was it? Yeah, the Concorde was a very hot thing, and these were planes that could cross the sonic barrier and become supersonic. For various reasons, they fell out of favor, and so those would be one situation where something like the Laval nozzle would be used. Okay, and I urge you to check out this URL. It's very interesting. Much of what we've discussed here is discussed here. Okay, let us now move over to discussing. So remember, the reason this is an astrophysical fluids course after all, and the reason we're discussing the Laval nozzle in such detail is because we want to see how the concept of a Laval nozzle is applied to astrophysical jets. Now, what are astrophysical jets? I need to show you pictures, right? And an application, I should say. It's not so much application. The concept of a de Laval nozzle is nicely applied here. That's what it is. Okay, so let me show you a picture. This, right? So what is this? These are cosmic jets viewed by the Very Large Array. And these are essentially what are called radio images. These images are images that are obtained at radio frequencies. Okay, and this is one picture, this is another picture, this is yet another, this is yet another. Okay, these are all different pictures. Let's just concentrate on this first one, for instance. Let's just look at this. Okay, this is good enough for our purposes. And what you have here is a nucleus. Okay, and from which you can see that there is matter. Even from the picture, you can see you can't see too much here, but nonetheless, it's evident that there's matter being squirted out like this. Okay, although I must say that what you're really seeing is radiation and not the gas or the plasma itself. Okay, what you're really seeing are photons. In particular, radio photons. That's what you're really seeing. Okay, so this is something to be kept in mind. And so, however, we will take the radiation to be a proxy for the matter. Okay, after all, if the matter here was not denser than the surroundings, okay, it would not appear brighter, isn't it? So it's in that sense that and radiation is always a two-body process. Generally, it goes the intensity of radiation generally goes as n squared. It's a two-body process. So the denser the matter, the more the radiation. So wherever you see excess radiation, you think that there's excess matter. That's what it is. So I just wanted to emphasize that what you're really seeing here is not matter itself, as you would in a lab. What you're really seeing here are photons that are being emitted and that are reaching telescopes of the Earth, and after a great deal of image processing, you obtain these spectacular images such as these, and from these you infer that matter is being ejected from the central point, which is often called the nucleus, in both directions. Okay, and out here, what happens is, this is what's called a hot spot, and this is called a blowback. These are called lobes. So most likely what's happening is this matter is being blown out in the form of a jet. The geometry, the picture, the reason we call them jets is pretty obvious from the picture. These do look like very narrow, very collimated jets, right? At this point, it's almost as if the jet is running into a wall. And when the jet runs into a wall, what happens? The matter splatters all over. Okay, and so this is really backflowing matter. Okay, and these are radial lobes, and these are hot spots. This is where the maximum dissipation takes place. All of this is not terribly important to us for the purposes of our present discussion. Our present discussion mainly centers on the fact that there are very collimated jets of matter that are being ejected from the central nucleus. That is it. And how is this happening? This is essentially what we want to discuss. Okay, and just to give you an idea, from here to here is often it depends. I mean, this is just one such jet. There are many such jets. Okay, and it's also been surmised that the speeds of these jets are often relativistic, and they're they're definitely supersonic, no doubt about it. Okay, yeah. So the other point I wanted to make is the extent of these jets. The extent of these jets is truly staggering. They are often they are several megaparsecs long. Huge monster jets from here to here would often be several megaparsecs. Okay, so the question we want to address, well, there are several questions that can be addressed in the context of astrophysical jets, such as the one we saw. Okay, one is how produced how do they remain collimated for so long, right? And you can see that, right? I mean, this jet remains incredibly narrow and collimated over really long distances. How long? Up, all the way to megaparsecs, right? Okay, so that's often the second question, and many other questions that can be addressed. For instance, are jets stopped? Stopped meaning like this out here. Okay, it seems as if the jet has run into some kind of a wall and it splatters out there, and it is essentially splattering all over, and that's what leads to these lobes, right? Okay, but however, in this case, we will confine ourselves just to this first question. How are they produced? And right. So you see, we will apply, obviously that's the reason we discussed the de Laval nozzle so much. We will apply concept of the de Laval nozzle. But you might ask how? How? I mean, how is the de Laval nozzle concept applicable here? The first thing to remember is that in our discussions of the de Laval nozzle, we prescribed and from the prescription we said, here's a converging nozzle, here's a diverging nozzle. In other words, we are prescribing exactly how the area varies as a function of x, right? And from this prescription we are deriving how the Mach number varies, or equivalently how the pressure. Okay, that's how we have been doing this. For astrophysical jets, we will do the opposite. We will prescribe in our discussion in discussing jets, we will do the opposite. We prescribe the pressure gradient and derive dA dx. Okay, and also the behavior of the Mach number. Of course, that's the whole point, isn't it? But the main thing is you are prescribing the pressure gradient, and from that it's as though the pressure gradient is equivalent to a dA dx. That's what it is. There's no physical nozzle as such. So again, let's be a little more specific. So what we're saying is that here is, I don't have a very good cartoon of this. So here is a central object. Okay, this thing, this central object, right? And around the central object there is really, you know, there is very dense medium. Okay, so what there's really dense medium, very high pressure medium. Okay, so there's matter being squirted out somehow. Okay, and there's very high pressure medium. Okay, and when it's squirted out, when it's initially being squirted out, the Mach number is less than 1. Okay, and there's very high pressure medium, and it's squeezing, you know, and this is subsonic flow, and you are, however, why is there very dense medium around? Because this is a very compact object, and compact objects always like to accrete matter. Stuff is accreting onto the compact object. So in the vicinity of the compact object, you would expect the density to be large and therefore the pressure also to be large. But as you move away, you would expect that the density falls off and therefore the pressure falls off. Okay, and that is essentially equivalent to a nozzle that is converging. Rather, I'm sorry, in the very vicinity, okay, as you transition from here to here, the density still keeps increasing up until some point. So that would be so dP dx is greater than 0 up until somewhere here. So this would be equivalent to a converging nozzle until somewhere here. Okay, so this would be something like a converging nozzle, and we know that converging nozzles for subsonic flows keep accelerating the flow. But as you move, so all this is very much in the vicinity of the central object, right? But as you move away from the central object, okay, away meaning sufficiently far away, okay, sufficiently from the nucleus, pressure drops. In other words, dP dx becomes less than 0, right? So, and dP dx becoming less than 0 is as good as a diverging nozzle. What you have to engineer is that the flow used to be subsonic until, and so the other thing is this is not to scale. This drawing is not to scale. Okay, this is very, very close to the object, and all of these are quite far from the object, from the central object. Okay, so very close. What's happening is the flow is subsonic, and you have to engineer in your mind. The concept is that around the time that dP dx changes sign from greater than 0 to less than 0, you have reached the sonic point. And so to the right of the sonic point, the flow now becomes supersonic. And once a flow becomes supersonic, the dP dx becomes less than 0, and that is as good as a diverging nozzle. And we know that a diverging nozzle serves to accelerate a supersonic flow. This is exactly like the Laval now, and that's what we want. We want the flow to keep accelerating and becoming more and more supersonic. Okay, more and more supersonic, so that it can travel to, it can accelerate, so that, essentially the bulk kinetic energy of the flow is keeps increasing, so that it can go on for long distances, as long as a megaparsec. Okay, up until the point where something else happens, the density of the interstellar medium increases so much that the flow cannot push against the density of against the interstellar medium anymore, and it comes to kind of a halt and it splatters all over. But that's not our concern right now. Our concern is trying to figure out how the flow becomes supersonic and how it keeps accelerating, and this is how. So you can see that in prescribing the pressure variation very close to the central object and very far from the central object, we are essentially creating a de facto de Laval nozzle. And so this is how the concept of a de Laval nozzle is very, very closely intertwined to this question: how astrophysical jets are produced. Okay, so that's all we have to say. Thank you.